Hi everyone, I'm Alex, and let's talk about whale fishing. Let me quickly introduce myself. So I'm one of the co-founders of Near Protocol. Before Near Protocol, I was working for a company called MemSQL. It's a sharded database. I was the first person to join MemSQL back in the day, back in 2011, when it was just 3 people and a Pomeranian in the garage. Right now it's 150 people with a multi-million ARR. Before MemSQL, I worked for Microsoft. Before Microsoft, I was participating in programming competitions called ACM, ICPC, where back in 2008, I got the gold medal, which will be relevant in a quick second. And Near Protocol, we started it last August. We started it as a public sharded blockchain, with the idea being that we looked at the space of all the layer 1 protocols, there are many of them being built, Definity, Algorand, Space Mesh, etc. Very few of them were sharded. And sharding is sort of important because if you think about, I like using Thunder as an example because Thunder is a pretty fast blockchain. Thunder can be up to 100 times faster than Ethereum. But the thing is that if Thunder gets adoption and blockchain in general becomes more used, the next thing we know is 2 years from now, we're going to be building Thunder replacement because we're at capacity again, because now we're consuming 100 times more. And sharding doesn't have this problem. Sharding scales with adoption. The more adoption you have, the more people using it, the more TPS you have. And as we started building sharding, we realized that in reality, building sharded blockchain today is very similar to building a huge stadium in the middle of the desert. Right? So we can have multiple stadiums being built there. And one will have 100,000 seats, another one will have 200,000 seats, and the third one actually will scale with the number of people there, but it will not matter at all until we actually have people who want to watch a game, right? And so from this perspective, we shifted the emphasis significantly towards building a very usable blockchain, right? So our current mission is to build a blockchain such that developing for it is as simple as building an Node.js application, and using it once an application is deployed should be as simple as opening a website. And initially, I wanted to talk about usability, but I changed the topic of my talk to sharding. And for sharding, I don't have a demo, but it wouldn't be a demo night if I didn't have a demo at all. So I will quickly show you our development experience. Just like if any of you built on Ethereum, I just want to show you how different could development experience be. And if you want to try it yourself, the website is near.dev. That's where we're hosting our development experience. It's an online IDE, which is a fork of an IDE called AssemblyScript. As you launch it, the first thing you will see, it will suggest you to fork one of the existing examples. And for this demo, I will use a guestbook example, which is a toy example on blockchain. And when you create it, it will pre-populate it with code. And so on the left, you will see all the TypeScript files is the smart contract. So the language near runs WASM on the backend. And so TypeScript is one of the languages which can compile to WASM, and that's the language we promote. Because any person who knows JavaScript can right away start building on WASM. And so effectively, the code, I'm not going to go through it too much right now, but the code is very close to what you would have if you built it in Node. And the beauty of it is that once you finish writing code, if you actually want to, first of all, you can write tests in Jasmine, which is a standard JavaScript framework. And if you want to test it, in one click, you can deploy it to a testnet, and it will run all the tests. And it will give you the results, which hopefully it will pass. Right, and it passes, right? So you can iterate very quickly. You change your smart contract. In one click, it gets deployed to an actual blockchain and run. And similarly, if you want to run it and play with it or share it with someone, again, it's a single click. In one click, you deploy it to the testnet, and you can start using it without having any browser plugins. You don't need to understand what the private key is, etc. You're just using it, right? And so that's a guestbook. I can post something, and it shows up. And if you want to test it with multiple users, you just give them the link, and they can open the same link. I guess you don't see it. Doesn't help much. Okay, you can give them the same link, and they will be able to interact with it themselves as well, using their own users. And so you can actually test multi-user deployment. And a particular beauty of it is, if something doesn't work, right? So let's say my smart contract doesn't work, and I don't know why it is. What I can do is I can, in the smart contract, so on the back end, I can log something. And I redeploy in one click again. And so now, as I log in, if I open my developer tools, which I hope they will be big, and I post something, you will see this one that I logged is logged in my browser console on the front end. And so now if something doesn't work in my smart contract, at the very least what I can do is I can near.log after every line, and I can bisect what is actually going wrong. Right? It would be even better if it was integrated into this debugger, which is the next step. It's not built yet, but this is something that is possible because WASM is actually something that a browser can run. Yeah, so that's a sneak peek at the development experience. Now let's talk about sharding. So first of all, why I think that Near is the team to build sharding? It's because it's one of the very few teams that actually comes from the industry. We have multiple people from MSQL. So besides me, we have also Misha, who is particularly famous for being one of the 9 twice ICPC champions in the world. And he was one of the 6 up until 2 weeks ago. We have lots of very experienced people coming from Google. And besides Misha and me, we have one more ICPC gold medalist. So it's a very strong team coming from the industry and not from academia. And historically, it happens that majority of production systems are built by people from industry. Okay, so let's talk about sharding. Let's say we have a blockchain. Without loss of generality, it could be Ethereum, it could be Bitcoin, and it's slow. So let's say it can process, actually, let me hide. It doesn't matter. Okay, so let's say it can process 12 transactions per second, or 7 transactions per second, and that's not enough. Let's say we want more. Let's say we want 36 transactions per second. What can we do? There's actually a very simple solution. If we want 36 transactions per second, what we do is we run 3 blockchains. And that's it. Scalability solved. There are, however, 2 problems with it. One is if they don't communicate, it's not the same as having one blockchain. Probably if you're running something on the blockchain and someone else is running something on the blockchain, you want those things to communicate. At the very least, you want to be able to pay anyone else on the blockchain, right? And the second problem, which is a way bigger problem, is that you can run one blockchain securely, but it is not necessarily the case that you can run multiple blockchains securely. As we all know, historically, with ETC being a good example, once you have multiple blockchains sharing the same security model but not sharing security, they become vulnerable, right? And the idea is, if you have one blockchain, you need to corrupt 50% of every person who maintains it, whether it's 50% of stake in the proof of stake or 50% of hash power. But if you have multiple blockchains, to corrupt at least one of them, you need 50% divided by the number of blockchains to corrupt at least one, right? And unless you have cross-shard communication, the remaining blockchains might not care much. So for example, Ethereum doesn't care much about Ethereum Classic being corrupted. But once your chains start communicating, that becomes a big problem. Imagine someone actually made some cross-chain transaction from ETC to ETH, and then ETC was reworked. Suddenly, there's something on ETH which is not backed by something locked on ETC. That's a huge problem, right? And so there's a solution to this problem which says, let's not allow people to choose what they validating, right? Let's not allow people to assign hash power to a specific blockchain or specific shard, or let's not allow people to assign their stake to a particular shard, and let's sample it randomly instead, right? So if you have a pool of, let's say, 1,000 people who are willing to be validators, we're not going to allow them to distribute themselves between shards. We're going to say every person will be assigned randomly to one of the shards. So at this point, if you control, let's say you control 1/10 of all the validators, there is no way for you to assign all the 10% of them to the same shard, and so you cannot really corrupt the shard. In reality, what will happen is that you will control 10% of validators in every shard, which does not help you in any way. And that works. If we're assuming that, so I used 30% here as an example for any sort of BFT consensus, but let's say if you use some sort of proof of work or any Nakamoto consensus and you're willing to have longer finality, you can use 50% here. But as long as less than the threshold is not corruptible, that works. Why does it work? Well, let's see. Let's see that you are a user of the system, so you're there on the far left, and you want to know what is the last block of the system. And so what you do is you go to the validators who are validating the blockchain today, and you're asking them, what is the last block? And the moment you see 2/3 plus one of them saying this is the last block, because you know that 70% of them are honest, you understand that in that signature you just received, more than 1/3 was honest, and so that has got to be the correct block, right? And what did they learn about the previous block on top of which they built the block? Well, they did the same thing, right? They asked the validator from the previous block, and at that point, 70% of validators were honest, right? And what did they learn about the block? They asked the previous guys, and by induction, we go all the way back to the genesis block, which by definition is correct. And so you can actually be absolutely certain the blockchain is correct just by seeing an attestation from the current validators on the latest block. That's beautiful. There's one problem, which is you cannot assume that 70% of people are not corruptible. If you actually think why people validate blockchains, they only have one motivation to do that. It's money, right? Every single person who mines Bitcoin, the only reason they do that, it's not some sort of gift to the society of securing Bitcoin, right? They want Bitcoins that they will get when they mine a block. And if you think about any proof of stake system, also one of the biggest motivations for people to validate is to get the reward, right? And so clearly they are corruptible by definition. They want money. At the very least, you definitely cannot assume that 70% are not corruptible. And so we're changing our assumption. Now our assumption is less than 30% of validators are malicious. And the remaining 70% are reasonable, meaning that they will do what we want them to do for as long as it's in their interest. But the moment they have a better option, they will do the better option, right? Well, that creates a problem, which is if we have 1,000 shards and the malicious actor has some interest in corrupting one of them, they can in some way identify the validators who are presently assigned to that shard. They can go to them and they can offer them more money than they would lose if they misbehave. So for example, in Ethereum today, in Ethereum design today for Ethereum Serenity, Ethereum 2.0, the stake is 32 ETH, and every shard has 100 validators. So you would go to a shard and you will corrupt 3,200 ETH. That's going to be your cost of corruption, plus epsilon, because they need to get more than what they spent, which is going to be way cheaper than corrupting the entire system. What can go wrong if you corrupt a shard? So let's say you actually successfully corrupted a shard and you have Byzantine majority in a shard. Technically, you can do a rework, you can fork, but every sharded blockchain today has a protection against it. It is called shared security, where you're producing blocks and shards independently, but there's one very secure chain. So let's say there's actually still Ethereum 1.0 running, and whenever you produce a shard block, you snapshot it to the Ethereum, and once it is on Ethereum, it's irreversible, right? So this way, in order to rework any shard chain, you have to rework Ethereum, which is very expensive. But if I corrupted a shard, I will not do a rework. What I will actually do is I will create a completely invalid block, right? So in this example, the block B is some block where the state transition is just applied incorrectly. So let's say before the block, Alice had 1 token and Bob had 0, and after the block, Alice has 0 and Bob has 1 million, and there was no transaction applied, right? And so naturally, any honest node, which is monitoring shard 1, will immediately just reject the block as straight up incorrect. But if we have 1,000 shards, it is presumed that nobody is actually validating all the shards. And so in particular, validators of shard 2 might as well not validate every block of shard 1. They might just not have capacity to validate every block of every shard, right? And so the only way for them to know that the block is valid is, as we discussed previously, they will look at the attestation from 2/3 of validators, right? And so they look at the attestation from 2/3 of validators on block C. There's an attestation, so they presume that the block is correct, and they accept the cross-shard transaction, which sends 1 billion tokens from the shard 1 to shard 2. And now shard 2, which is completely valid, at no point it was corrupted, suddenly has tokens which never existed, right? And so one solution would be for shard 2 to actually validate the entire shard 1 chain. But imagine there is 1,000 shards and all of them sending transactions to all others. It becomes completely infeasible for every validator to validate every other shard. There's a solution again, and a solution called a fisherman, with the idea being if there's at least one honest validator, right? So we're not talking about 1/3 or 50%. If there's at least one honest, that one honest validator will obviously notice that the block B is incorrect. And so what they do is they're fishing. They go into shard 2, and they're saying, you see you have this cross-shard transaction coming from shard 1, but here's the thing, the block is invalid, and here's a very small cryptographic proof that it is invalid. And what happens is, in reality, fishermen will not fish to shard 2. They will actually fish to that very secure global chain, and the global chain will just slash all the validators on shard 1 and will undo all the damage they have done. The problem is that imagine our previous assumption that every shard has honest majority, right, and they never corrupted. Then the moment we see the attestation on block C, we can immediately process the second part of the transaction, right? So imagine this transaction, that the cross-shard transaction that goes from block C to block Y is something that spends Alice's money on block C in shard 1 and adds money to Bob on shard 2. Without fisherman, we would just immediately process it, right? We would the moment the block C is produced and this cross-shard transaction reaches the second shard, they will see the transaction, they will see attestation on the block, they will immediately apply it in the second block. And so cross-shard transaction, the time it takes for cross-shard transaction will be just one block, which is, let's say, 6 seconds, right? Now with the fisherman, this delay actually needs to be very long, because that honest validator, they need to realize that the invalid block was produced. They need to identify it, then load it, verify it, which takes time, actually prepare a proof that it is incorrect, send it, ensure that it was actually received on the other side, right? It will take a lot of time. So how do we solve it? Well, the easiest solution is to say that shard 2 actually will not execute the second part of the transaction until certain sufficiently long period passed, after which they're sufficiently certain that no phishing attempt will be made. That's a disastrous approach, because your cross-shard transaction is now easily ours. The second approach, which is slightly more reasonable, is to say that imagine on shard 1 at some point a block was created which was invalid. So the very first red block in shard 1 is invalid. And then a few more blocks were produced on top of that, nobody noticed. And then in the block in which it says A1, that's an initiation of a cross-shard transaction, which reaches the second shard. And on the second shard, it is immediately applied. So immediately as they receive A2, they immediately apply it. But then if phishing attempt happens, if a fisherman at some point actually says, oh, you know what, shard 1 had an invalid block, what happens is shard 1 forks out naturally because the chain is invalid, but also shard 2 will also fork out. Effectively, what we're saying is that if you applied a transaction which originated from an invalid block, your block is also invalid, right? And so as phishing attempt happens, all the affected shards fork out. And so now the cross-shard transaction time is actually very low, and the finality, like let's say you some sort of an exchange, and you actually happen to verify both shard 1 and shard 2, then your finality is instantaneous. Because if you know that shard 1 is valid and you know that shard 2 is valid, you actually don't need to wait for phishing attempts, because you know there's not going to be a phishing attempt, right? And from here we can, that's just a completely different model to think about it, but at that point you can start thinking about it as not multiple chains, multiple shard chains. You can think of it as a single chain with huge blocks where nobody actually sees the content of the entire block. Everybody only observes a part of the block, right? And then the same thing applies, right? So this is a huge block in the global chain where in shard 1 something invalid was applied, shard 2 still valid up until now, then another huge block produced, and the cross-shard transaction happens here. Now both of them are invalid. At some point fisherman fishes, and you can think of it as just this global chain forking out, instead of thinking of it as multiple shard chains forking out. Cool. So now let's quickly talk about how fisherman would actually prove that the block is invalid, right? Because shard 2, no validator in shard 2 actually has the state of shard 1, right? It is completely infeasible. Like today, Ethereum state is 100 gigabytes at 12 transactions per second, right? It is unclear if the relationship between the TPS and state growth is linear, but it is probably close to linear. That means that if you have 1,000 transactions per second, you will get to 100 gigabyte state within days, right? And so it is infeasible for everyone to have the full state. Everyone has just the state of the shard. So the shard 2 has only state of the shard 2. Shard 1 has the state of shard 1. So by the time when fisherman sends the phishing attempt, they need to prove to shard 2 that block B is invalid without shard 2 actually having to download the state of the shard 1. So how would you prove to someone that block in Ethereum is invalid without them having the state? Because the only thing that block contains is the transactions, right? So what you do is use this construction called Merkle tree. And a Merkle tree, so this is the whole state of the entire system, or like of the shard. And what you do is you compute the hash. So on the very bottom, you have the actual state. And on every level above, you have a hash that hashes 2 of its children. Does that make sense? And so what happens is, at the very top, you have the root of the tree, which also has a hash. And now let's say I want to prove to someone, and so that hash is snapshotted in the block. All right, so this is how Ethereum or Bitcoin work. They all have this Merkle state root in the block. And now let's say I want to prove to someone that the state, you see this like little highlighted green blocks at the bottom. I want to prove to someone that the values there are what I'm saying they are. What I'm going to do is I'm going to send to the people those values, and also I'm going to send them all the remaining highlighted green hashes. And from here, the recipient can actually verify that that information is sufficient for them to recompute the root. Because if you think about that, the 2 green blocks at the bottom, they're sufficient to compute the hash of the thing right above them. That and the hash I send them is sufficient to compute the hash right above that. And that thing and the hash on the far left is sufficient to compute the root, right? And so if the tree was taller, in reality, I would only have to send log n hashes to prove to someone the state at the bottom, right? And so now for me, to prove that the block is invalid, all I need to do is to find the first invalid transaction. And let's say that the state is snapshotted between every 2 transactions. And then I'm just saying, here's the invalid transaction. Here is the state it touches. I don't need to send the full state, just the state the transaction affects. And here's the Merkle proof of the state before. And then anyone can, the recipient of the phishing attempt can now recompute the Merkle root after and confirm that it does not match what the incorrect block contains, right? There's a problem with that. If we have corrupted a shard, right? So let's say validators change over time. And so at some point in the shard, the validators are corrupted. And so 2 of them are corrupted. There's a couple honest ones, but there's sufficient number of corrupted ones to create the attestation, right? So 2/3 plus 1 are corrupted, and they will create an attestation on the block. They actually never have to share the full block. That's a huge problem. What they will do is they will share the header of the block. They will say, this is the Merkle root. This is the previous block. This is attestation that the block is valid. And that's all they're going to send. They cannot send the full block. The blocks, if all the blocks were passed around between all the shards, that would completely congest the network, right? They're only exchanging headers. And so they would send the header to a light client, where light client could be a person who uses it, or it could be a validator of another shard that receives that block. And so now a fisherman needs to prove that that block is invalid, but they cannot prove that the block is invalid because they never saw the block. The block was never actually shown to anyone, right? Because the validators, the malicious validators, could attest to the block without, they know the block, but nobody else does, right? Does that make sense? So effectively, they can hide the block from everybody. And the problem is that, first of all, next validators cannot continue building the blockchain can stall to begin with, but also they can, if they remain validators, they can continue building the blockchain without revealing the blocks, and so nobody will be able to challenge the invalidity. Cool. So data availability is significantly more complex problem than state validity that we discussed before, the invalid state transition, because you can prove that the state transition is invalid. You cannot prove that data is unavailable. Like if you think about it, if I try to go to someone and say, you know, this file does not exist on the internet, by the time they check if it exists, it can exist, right? You cannot prove that something does not exist, right? You cannot prove that God does not exist, for example. Cool. So there's some research, not very much, on this topic. One of the more prominent papers is the paper from Mustafa from ChainSpace, and it became quite famous because of another co-author on that. So that paper explains a very, very complex construction for data availability proofs. There are more easier constructions. One of them is used by Polkadot. They all rely on the same underlying idea. The underlying idea is the following. Imagine you have a block. You cannot send the full block to all the people. That would be too expensive. What you can do is you can split it into parts. Like let's say we split it into 100 parts and send one part to each part to different person, right? So now 100 people collectively have a block. The problem is that if at least one of them does not share the part, the block is again unavailable. And so what you do, you use this technique called Erasure Codes, where you start with some amount of data. So the left 4 is the original data. And then you build in a specific way more data such that, let's say here I have 8 parts. You can build it in such a way that any four of them are sufficient to reconstruct the block, right? And so what you do is, as you have a block, you split it, like let's say block is x bytes. You create 3x large erasure code such that any 1/3 of the chunks into which you split it of the parts is sufficient, right? And then you send it one to each validator. So then, for as long as 2/3 of validators are honest and 1/3 of them are available, you can reconstruct the block, right? So that can prove your data is available. You still cannot prove it's unavailable, so it's not a full solution, but it's at least we're getting there. And so after all this, we started answering some questions, but we actually ended in the state where we have more questions than we had before we started. Right, so first of all, we actually still have no idea how to ensure state validity under adaptive adversary. We didn't figure out how to ensure finality with fishermen, right? If all the shards can fork out at some point, that's a disastrous situation. For example, Ethereum today has an invalid block a few years back, right? The DAO fork. We cannot fork the entire Ethereum just because we all agree that that block is invalid. And also we still, we have some idea how to do data availability, but it is unclear how to make people accountable. And so that's something. Now let's actually finally talk about whale fishing. So whale fishing is the new sharding design that we did not commit to yet, but we're actively developing it right now. We published it on ETH Research a couple days ago, so feel free to join on NightShade if you find it interesting. So let's get a quick overview of it. So the first role, it has 2 roles. The first role is block producers. The block producers are people who stake a lot of money. And so if we call things with the names they actually are, those would be whales. Right? And so whales are producing blocks. They don't have to be whales, they can be sampled, but for simplicity, let's say it's whales. And we will model it not as multiple shard chains and one secure chain. We will model it just as a single chain, where every block contains data for all the shards. It's just that nobody ever observes the full block. People always just observe part of it. People always observe parts of it. And let's say we have 8 validators, 8 block producers, sorry, and we have exactly 8 shards. So for simplicity, we're going to say we have as many block producers as we have shards. And we will assign groups of 4. So we will assign the first 4 validators to the first 4 shards, the next 4 validators to the next 4 shards, etc. And they will just take turns producing the parts of the block that correspond to the shard. We call them chunks, right? So here, each color represents a different validator. And you can see, like, if you follow the pink one, the one that starts at the position 5 in the very first block, you can see it produces the chunk for the shard 5 in the first block, for the 6, for the shard 6 in the second, 7, 8, and then again 5, 6, and they continue rotating, right? It would have been simpler if every block producer was just assigned to a single shard. The problem would be that if one block producer goes offline, the entire shard stalls. Here, for a shard to stall, you need 4 block producers to go offline, and you can configure it, right? If that is too likely, you can make 10 block producers rotate over 10 shards. And then we use that technique about erasure codes. Whenever block producers produces a block, they compute the erasure code and they send. So there's 100 validators, let's say, or like let's use 8 from the previous example. There's 8 validators. They will create 8 parts such that any, how many is that? 2? Any 2 are sufficient to reconstruct, and they will send 1 part to every validator. And so at this point, for as long as at least 2/3 of validators are honest, any block will be retrievable. And after that, and effectively, for every block, they reach a consensus. They can use Tendermint on any consensus. They need to reach a consensus on which blocks effectively are available, which chunks are available, right? So what happens is, for every block, they will all gather together, and each of them will say, this is my chunk, and I sent you part of it to each of you. and they will all only attest to a block if they actually have their part of every chunk that is included in the block. And so what it means is that if the block has 2/3 of signatures, that means that every chunk which is in the block is retrievable. Does that make sense? Cool. Now, the problem is there is 4 validators per shard, and they're known in advance, right? They're corruptible. It's very easy to go out there, identify the 4 block producers, and just pay them more than they staked, which would still be, as again, significantly cheaper than corrupting the entire system. And so what we do is we have fishermen who fish whales. So it's whale fishing, right? What fishermen do, there's significantly more fishermen. Let's say there's 10 times more fishermen or 100 times more fishermen than block producers. And what fishermen do is, so let's have a concept of an epoch. The epoch is period of time when whales and fishermen do not change, right? So every epoch we might want to resample them, but within the epoch they don't change. At the beginning of the epoch, every fisherman uses a random number generator, it's called verifiable random function. It's something that a person who has a private key, they can use some sort of randomness and the private key to generate some random number that only they will know. So knowing the public key is not sufficient to generate the same random number. But later they can prove the random number using just the public key. Does that make sense? So effectively at the beginning, I'm using, like, I roll a die and it tells me 6 based on my private key. So I know the 6, nobody else does. And then sometime later I can say, oh, that was actually 6 and here's the proof. And everybody will be able to verify that it was actually 6. And so what we do is every fisherman uses VRF, and they get a bit mask of the shards they will be verifying. So they sample 4 or 10 shards they will be verifying, and they're not telling anyone which shards they're verifying, right? And so what it gives you, this idea comes from, this is not a novel idea. Algorand uses it, and Ouroboros, the Cardanos or /Codes consensus uses a similar idea. The idea is that if you don't know whom to corrupt, it's significantly harder to corrupt. It's still possible, but it's significantly harder because you don't know whom to reach out to. You effectively have to broadcast your corruption request and expect people to go to you and prove to you that they actually people who possess the power you need. So what you do next is, on every epoch, there is a block that is being produced for multiple shards. And so let's say, so the bit mask was 001001, so we're validating shards 3 and 6. And so what you do on every block is you download, and you can always download the blocks, right, because data availability is ensured. You download the chunks for the shards you're validating, you validate them, but you're not signing just on their validity, you're signing on the entire block. And so nobody just from your signature can infer which shards you validated, right? So that's not a sufficient, that's not sufficient yet. Why? Because let's say at some point one shard was invalid, right? And so the biggest problem we're trying to solve here is that the fisherman might choose not to validate anything. They might choose just to sign blocks and get their reward, right? And then we don't get any security from them. So we need some way to actually know that they didn't do that. And because there's so many of them, we cannot have each of them produce a unique proof of their computation. Just verifying those proofs would be expensive, and then people will just opt not to verify proofs. And again, we're not getting the security. So what we're doing instead is, what fishermen do is so let's say the full block 1 was produced, and so fishermen need to download state, they need to validate it. First of all, that will take time, right? So there is no way for fishermen to, so let's say we allow 10 blocks to pass before they pass their verdict. And so within 10 blocks after block 1, they need to commit to a message, either yay or nay. What commitment means is that they're storing something on the blockchain from which it is impossible to recover what the message was, whether it was yay or nay, but they will be able to prove later to you what it was. Does that make sense? Right, and so within 10 blocks they're committing. Yay means whichever shards I was assigned to, I'm still not saying what shards were, but whatever shards I was assigned to, they were all valid. And then later, by the block 20, I need to reveal that. I need to say, oh, it was actually yay, right? And at that point, so effectively I will be posting, at some point I will be posting 2 messages per block. I will be posting commitment for something within last 10 blocks and my reveal for something that was, let's say 20 blocks ago. Now what happens is, and if I post nay, I actually say which block was incorrect, right? And then as I reveal nay, I also reveal the proof. And so what happens is, let's say that we have two fishermen, and fisherman 1 is lazy, they're not validating anything, and fisherman 2 is actually proper fisherman. Or fisherman 1 could be malicious, they actually might be intentionally trying to fish incorrectly. And so block 1 was invalid. So block 1 had an invalid state transition. All the block producers were corrupted. By block 7, the first fisherman commits to yay. Fisherman 1, either because they're lazy or because they're malicious, they commit to yay, even though the block was invalid. And fisherman 2 commits to nay. By block 13, for fisherman 1, it's too late to say nay, because they already committed to the outcome yay. And so what fisherman 2 does is they reveal nay. And what happens when someone reveals nay, and it is proved to be the case, so they reveal nay and they provide the proof that the block was invalid, at that point, all fishermen have to immediately reveal their bit masks. Right, so if you don't reveal a bit mask, you get slashed. Effectively, concealing the bit mask is, presume that you're doing that because you had the bit and you're trying to hide. And so if you don't reveal the mask, or you reveal the mask and you have 1 in the bit mask for the chart, you get slashed. That effectively means, unless you also reveal nay, obviously. If you reveal nay, it's all good. That means that you did your job properly. But if you cannot reveal nay, or you cannot reveal the mask, you get slashed. And so what it gives you is that for a lazy fisherman, they're effectively taking chances that all the blocks are actually correct. The moment there is an invalid block, they will get slashed because they didn't catch it. And the malicious fishermen, because notice that when fishermen were sampling bit masks, there was no way for us to tell the exact number of fishermen assigned to every shard, right? Because every fisherman sampled shards independently. Every shard in expectation will have, let's say, 4 fishermen or like 40 fishermen, but we don't know the exact number. And so even if you, as a malicious actor, managed to corrupt, let's say 40 of them, so you identified 40 of them, they revealed their bit masks to you, you still don't know if there is more, right? That's actually very similar to something that Fluence just presented a few minutes ago. And so because of that, as a fisherman, you're always risking to be slashed if you're not doing your job properly. Cool. So quick overview of why this design, the beauty of this design. There are a few things that it solves that are sort of problematic in sharding today. Problem number 1 is that adaptive corruption is very hard. In the sense that if you want to corrupt a full shard, you cannot reach out to people who are validating the shard, you don't know them. So your only option actually is to broadcast your intent to corrupt the shard and have people reach out to you and prove to you that they're validating the shard, right? But because you broadcasted it, you brought attention to yourself. At this point, the entire system knows that the corruption is about to happen, right? Second, the data availability story is better. It's still pretty bad in the sense that, yes, if 2/3 plus 1 people are providing you block parts, it's all good. But we're saying that block producers can be corrupted, meaning that if they are corrupted, the data can actually become unavailable. So more progress needed on that side. And so in terms of finality, effectively what we're saying is, if the phishing attempt happens within 20 blocks, then the system can roll back, right? So you know that you need to wait for 20 blocks to get the full finality. If within 20 blocks, phishing attempt did not happen, at that point, blockchain went so far that that forking out will actually cause quite a bit of damage. So at that time, effectively the proposed behavior is to keep the invalid state and use on-chain governance or off-chain governance to actually deal with that. So either apply one-off state transition, which is custom, or just say, well, we didn't fish it, so the minted tokens are there. And so in this case, effectively, you're having 20 block finality, but you have a risk of having to resort to some sort of governance. But effectively, that's what, if someone mints 1 billion tokens, you have to resort to off-chain governance. Cool. So that concludes my core part of my presentation. A little bit of information about what we do. Besides building NEAR, we have another project called Whiteboard Series, where we invite other protocols to our office, or we go to their offices, and we talk for 1 hour about their technology in front of the whiteboard. And those are very deep technical conversations. The first one was with Cosmos, who's going to be talking right after me. And today we have Cosmos, Ethereum, Polkadot. We're going to be releasing Coda and Quark chains shortly with Fluence. And there's a total of 15 of them, MakerDAO. And that's a great resource to learn about those protocols. Usually this 1 hour video will give you way more information than reading a white paper. And the link is near.ai/WBS, whiteboard series. If you want to play with Near, if you like my demo at the beginning, the IDE is near.dev, and we have incredible documentation at docs.nearprotocol.com. Finally, as I said, we insanely committed and devoted to usability. The only other thing we equally devoted is vanity metrics, so please follow us on Twitter. Cool. Thank you. Questions?
What's your favorite application built on Near so far?
We don't have many applications built on Near, but it's obviously going to be MemeGen. Actually, there's a website built with Near, so check it out. It has few applications built on us. Any other questions? Awesome. Thanks a lot.